Hello everyone. In the series of videos related to the chapter Electric Charges and Fields, today we will be discussing about electric dipole moment and electric field intensity on the axial line of the dipole. Okay. What is electric dipole? Okay. What is electric dipole? Electric dipole is a pair of equal and opposite point charges, let us say q and minus q, separated by a very small distance. So, it is a system of equal and opposite charges q and minus q. Let us say this is minus q charge here and this is plus q charge here. They are separated by a small distance and the distance, let us say, is denoted by 2a. Okay. So, two equal and opposite point charges, these are point charges which are separated by a small distance, let us say 2a, forms an electric dipole. So, what is 2a? 2a is said to be the length of the dipole. 2a is the length of the dipole. Okay. So, the length of the dipole is equal to 2a, right. And what will be the total charge on the dipole? Now, according to additivity of charge, that is the property of charge, if you find out what is the total charge on the dipole, total charge on the dipole will be nothing but it will be equal to 0, because minus and plus q, minus q charge and plus q charge. So, the total charge on the dipole is 0. The electric field due to the dipole is not 0. Total charge on the dipole is 0, right, but the electric field of the dipole is not 0, because the two charges minus q and plus q, they are separated by some distance, right, they are separated by some distance, and electric field due to them when added is not equal to 0. So, what are we going to do is, we will find out what is the electric field at a point due to minus q charge, what is the electric field at a point due to plus q charge, right. And we will use electric field intensity at a point due to point charge over here, the formula for that, and then with the help of principle of superposition we will find out what is the total electric field at a point due to the dipole, right. So, the total field due to the dipole is not 0, but the total charge on the dipole is equal to 0. What are the different examples of dipole? Dipoles are very common in nature. For example, molecule of water, it is a dipole. Alcohol, these are all dipoles. Okay. That is, they are having plus q charge and minus q charge. They have permanent dipole moments because they centers of their positive charge does not fall exactly over the centers of their negative charge. Okay. So, when the centers of the positive charge and the center of the negative charge are not coinciding, then the molecule has a permanent dipole moment. They will have a permanent dipole moment in that case. Okay. So, as you can see in the diagram over here, there is minus q charge, there is plus q charge, and the two charges are separated by a small distance 2a, which I had shown you in this diagram also, and this forms an electric dipole. This forms an electric dipole. I will tell you what is P over here, which is written in the next slide. I will tell you what is the meaning of this P vector also. Now, we move on to electric dipole moment. What is electric dipole moment, right? Now, electric dipole moment, it measures the strength of an electric dipole. It measures the strength of an electric dipole. It is a vector quantity. It is denoted by P vector. This P is a small p. It is denoted by P vector and it is a vector quantity. Mathematically, P vector is equal to the product of magnitude of either charge, the product of the magnitude of either charge and the distance between the two charges. And the distance between the two charges, we write it down P vector as Q, magnitude of the product of either charge, into 2A vector, right. This 2A, we are considering it to be a vector where 2A is nothing but it is the length of the dipole or the distance between the two charges. Direction of this P vector is always considered to be from the negative charge to the positive charge, right. It is taken to be from the negative to the positive charge, right. It is taken to be from the negative to the positive charge. Okay. So, P vector, if this is minus Q, right, and this is plus Q, the two charges are separated by a distance 2A, then P vector is nothing but it is in the direction from minus Q to plus Q. Ideal dipole. What do you mean by ideal dipole? When the size of the dipole is very small, right, and the charge Q gets larger and larger, keeping the product P is equal to Q into 2A constant, then we arrive at what is called an ideal dipole. So, basically an ideal dipole is when the size of the dipole is very small, or it is the smallest dipole. Okay. So, that is considered to be an ideal dipole. Now, we move on further and talk about the physical significance of electric dipole. Okay. Atoms and molecules as a whole, as you all know, are electrically neutral in their ground state, and they have an equal amount of positive and negative charge. You know, atom is electrically neutral, it has equal amount of positive and negative charge. In a system, even though the algebraic sum of all the charges is 0, it does not necessarily mean that electric field produced by the system is also 0 everywhere. That is what I told you. Though the charge, total charge on the dipole is 0, but the electric field due to a dipole is not 0. Matter, which is made up of atoms and molecules, is electrically neutral. Now, if the center of mass of positive charge coincides with that of the negative charge, then the molecule is behaving as a non-polar molecule. That means the center of the negative charge and the center of the positive charges, they are both coinciding, right? They are both coinciding, then the molecule behaves as a non-polar molecule. But if the center of mass of the positive charge, it does not coincide with the center of mass of the negative charge, then the molecule behaves as a polar molecule, right. Now, these polar molecules, they have what is called permanent dipole moment. So, in that case, what will happen is the center of the negative charge is not coinciding with the center of the positive charge, right, and there is some gap in between, there is some distance in between, and therefore, these molecules are said to have a they are said to be polar molecules, and they have a permanent dipole moment over here, which is randomly oriented in the absence of any electric field. If there is no electric field, then these dipoles are randomly oriented. When they are placed in an electric field, then what happens is they all align themselves in the direction of the electric field, because electric field is from the positive, it is in the direction from positive to negative. And what is the dipole direction? Dipole moment is directed from negative to the positive charge. So, when this dipole is placed in an electric field, they will all try to align in the direction of the field. So, okay, so suppose the dipole is placed in an electric field. Suppose this is the electric field which is present, this is positive and this is negative. So, when they are placed in electric field, these dipoles will all align from the in this particular direction, that is from the negative to the positive charge. They will all align in the direction of the electric field. Electric field is in this particular direction. So, they will all align in the direction of the electric field, and this results in the development of a net dipole moment. Okay. So now they are not randomly oriented, so they will have a net dipole moment. So this particular piece of material is now said to be polarized. Okay. So we have understood what is electric dipole, we have understood what is electric dipole moment, and also physical significance of electric dipole. Now we move further and talk about what is electric field intensity on the axial line of the dipole. What do we understand by axial line of the dipole? So let me tell you what is axial line. This is minus q charge, let's say this is plus q charge. This forms an electric dipole. The length of the dipole is 2a. The dipole moment is directed from negative to the positive charge, right? So this is p vector, which is I have told you in the previous slide. This is nothing but P. If I write down the magnitude of P, this is Q into 2A. What is axial line of the dipole? Axial line of the dipole is the line joining the minus Q and plus Q charge along the axis of it, right? This is said to be the axial line of the dipole, extended on both the sides. So as well as on this side, this is axial line of the dipole, extended on the right side of plus Q, this is also axial line of the dipole. So the axial line of the dipole is line passing through the positive and negative charges of the electric dipole. So we have again considered a system of minus q and plus q charge separated by a distance 2a. Okay. So now over here, let me tell you that I am considering over here a point P which is on the axial line of the dipole, as seen over here in the diagram also. We are considering a point P which is on the axial line of the dipole, where we are trying to find out the field intensity. Okay. Let this point P, this is, let's say O is the center of the dipole, and let this point P be at a distance r from the center of the dipole. Okay. So let this distance OP be equal to r, and O is the center of the dipole. Okay. So this much is clear, that P is a point on the axial line of the dipole where we want to calculate the field intensity due to the dipole. So now what we have to do is, we have this particular diagram again, the same diagram which we had in the previous slide, and what we do is, we have this minus q, we have the plus q over here, they are both separated by a distance 2a. This is the point P on the axial line of the dipole. Okay. This is the point P on the axial line of the dipole. O is the center of the dipole, and OP is equal to r. Okay. Let us say this point where minus q is placed is A, and the point where plus q is placed is, let's say, B, and small p is nothing but the dipole moment vector. It is directed conventionally from negative to the positive charge. Now what we have to do is, we have to find out what is the field intensity at the point P due to this minus q charge at A. Minus q and plus q are the 2 point charges, and we have already done the expression for the field intensity at a point due to a point charge. So what we have to write down over here is, the field intensity at the point P, the field intensity at the point P due to minus q charge at A, due to minus q charge at A. So that we denoted by, let's say, EA, and that we write it down as 1 upon 4 pi epsilon naught. I am only writing down the magnitude over here. I will tell you the direction separately. 1 upon 4 pi epsilon naught q upon, what is the distance between minus q and p charge? You can see this is the between O to P, it is r, and this distance between AO, it is A, and this distance between OB is also equal to A, right. So because O is the center of the dipole. So what is this? AP squared. And what is AP squared? AP squared will be equal to 1 upon 4 pi epsilon naught q upon r this is r, OP is r plus of A whole square, right. The expression what we are using is electric field at a point due to a point charge, that is E is equal to 1 upon 4 pi epsilon naught q upon distance square, right, q upon distance square. Okay. So, whatever is the distance square of that. Have you understood this? And what will be the direction of this field intensity EA? The direction of this field intensity will be along PA, because how do we find it out? When this is the field at a point, we find out by placing a unit positive charge. So, unit positive charge is P at the point P is Q naught, let us say, and this is minus Q and this is minus Q charge. So, there will be a force of attraction. So, the field EA will be directed towards the charge minus Q. So, EA will be along PA, right, as you can see over here EA will be along PA, right. Okay. Similarly, now we will write down what is the field intensity at the point P due to this plus Q charge at B, due to this plus Q charge at B. So, when we write that down, again we have this EB, we denoted by EB now, we write it down as 1 upon 4 pi epsilon naught Q, we are writing down the magnitude, Q upon, now this is BP squared, right, BP whole squared. And what is BP? BP is nothing but, as you can see over here, this is BP is nothing but this will be equal to R, this whole distance is R, OP is R and this distance is A, OB is A. So, BP will be nothing but R minus of A we will write. So, this is Q upon R minus of A whole square, right. So, we get this. What will be the direction of EB? The direction of EB will be along BP produced, right, along BP produced. So, direction of this will be along BP produced. Okay. So, as you can see over here, the direction of EB will be along BP produced. So, you can see over here this is EB, okay, right. Now, these two fields EA and EB, these two fields you can see over here, EA is along PA and EB is along BP produced. These two fields EA vector and EB vector, these are collinear vectors, they are both collinear vectors and are acting in the opposite directions, they are acting in the opposite direction. And you can tell me which is bigger, EB is this 1 upon 4 pi epsilon naught Q upon R minus of A whole square, right, and EA is equal to 1 upon 4 pi epsilon naught Q upon R plus of A whole square, and EB is equal to 1 upon 4 pi epsilon naught Q upon R minus of A whole square. Which is bigger? Now, EB is bigger than EA. So, what is the net field at the point P? The net field at this point P we have to find out. The net field at the point P is equal to, let us denote it by E or EP, that is equal to EB minus EA, and that is equal to 1 upon 4 pi epsilon naught Q upon 1 upon 4 pi epsilon naught 1 upon R minus of A whole square. I took Q upon 4 pi epsilon naught outside, minus of Q upon R plus of A whole square, right. This we have written it down, correct. And after solving it, you can solve it, right, and if you solve it, you will get over here, this is Q upon 4 pi epsilon naught, right. This if you solve, you will get 4AR upon R square minus A square whole square, right. If you solve this, this will be R square minus A square whole square, Okay. So, we get this q upon 4 pi epsilon naught 4 a r square minus a square the whole square. Now, this can be also written as EP can also be written as q upon 4 pi epsilon naught 4 a r can be written as over here 2 r into 2 a upon r square minus a square the whole square, r square minus a square the whole square. Now, what is q into 2a? Q into 2a already we have defined it as electric dipole moment, right. So, therefore, EP can be written as 2p, q into 2a is p and this is 2 over here and this is r upon 4 pi epsilon naught r square minus a square whole square, right, r square minus a square whole square. So, this expression is nothing but 2pr upon 4 pi epsilon naught r square minus a square the whole square. Now, here they have written it down as 2kpr. We can even write it down like this because k is equal to electrostatic force constant which is 1 upon 4 pi epsilon naught, 1 upon 4 pi epsilon naught. So, this can also be written as EP can also be written as 2kpr upon r square minus a square the whole square, right. This is also the expression. What will be the direction of this EP? The direction of this EP, because EB is greater than EA, so the direction of EP will be the same as the direction of EB. It will be the same as direction of EB, that is BP produced, right. So, the direction of EP will be the same as BP produced. Now, we have a special case related to this. Okay. What is the special case? The special case is that when the size of the dipole is very small as compared to the distance where we are calculating the field from the center of the dipole as compared to the distance, let us say r. So, when 2a, the size of the dipole is very small as compared to r, right, then in that case this a over here in the denominator it can be neglected, and if you neglect this then what do you have over here? This is a special case, or we say, I will tell you just now, it is the special case which is called relation for short dipole, that is this is 2 into k into p, right, upon r cube. And how do we get r cube? Because you will get, okay, I will show it to you. This is equal to, this is r, right, and this is r raised to the power of 4 because 2a is much smaller than r. This is neglected, a is neglected over here. So, you get r square whole square, that is r raised to the power of 4, and this r and this 1 r over here gets neglected and you are left with r cube. So, you get the expression EP is equal to 2kp upon r cube, right, 2kp upon r cube, or if you want to write down the expression for k, that is 2p upon 4 pi epsilon naught r cube. Okay. So, that can also be written, EP can also be written as 2p upon 4 pi epsilon naught r cube, right, and the direction of this EP will be along BP produced, right, will be along BP produced, right, it will be along that. And this is the expression for the field intensity at a point which is on the axial line of the dipole. Axial line of the dipole means the line joining the two charges minus q and plus q, which forms the dipole. Okay. If you have any questions, you can write it down in the comment section, and if you want to see more such videos, please hit the subscribe button like and share the video. Thank you.